All right, welcome. If you are grinding through your CFA Level 2 prep, you know that bonds with embedded options are a huge deal. So today, we're going to build out your toolkit and really zero in on the essential risk measures you absolutely have to know cold for the exam. So let's just dive right in. A regular plain vanilla bond? It's predictable. You know the cash flows, end of story. But when you introduce a call or a put option, that bond suddenly gets a mind of its own. The cash flows are no longer set in stone because they hinge on what interest rates do in the future. And this is exactly where your standard risk measures just fall apart. It's why we need a much more sophisticated set of tools.
So, to really get a grip on these more complicated bonds, we've got to start with a benchmark, a point of reference. And that benchmark is always the simple, option-free, straight bond. Its behavior is our baseline. And the secret to all of this is understanding exactly how callable and puttable bonds stray from that baseline.
Okay, our first and honestly most important tool is effective duration. Now, you might remember modified duration, but that only works when cash flows are fixed. Effective duration is built for uncertainty. It's the universal Swiss Army knife for measuring interest rate risk, and it works on every kind of bond. That's why you can bet you're going to see it on the exam. And this chart right here, this visualizes the whole game. As interest rates move around, you can see the effective durations for these bonds start to go their separate ways. The straight bond's duration is pretty steady, but look at the callable and puttable bonds. Their durations change, and they change a lot. That is the embedded option doing its thing, and it completely changes the risk profile of the bond.
So here's the key relationship, the thing you have to burn into your memory. For a callable bond, when rates fall, its price gets closer and closer to that call price. The upside gets capped off, and its duration shrinks. It starts acting like a much shorter-term bond. Now, for a puttable bond, it's the mirror image. When rates rise, the bond's price falls towards the put price. Its downside is protected, and again, its duration shortens. This lopsided, asymmetrical behavior is the theme you'll see over and over again.
You know, duration is fantastic, but it's really just a straight-line estimate of a bond's price change. We all know the real price-yield relationship has a curve to it. And that curvature? Well, that's what convexity measures. And for bonds with embedded options, that curve can bend in some really strange and frankly dangerous ways.
And this slide lays out a huge risk you absolutely need to nail for the exam. A puttable bond? It always has positive convexity. That's good. It means your price gains from a rate drop are always bigger than your losses from a rate rise. But a callable bond can have negative convexity. This is bad. It happens when that call option is getting close to being in the money. It means for the same change in rates, the price will fall more than it will rise. That's a really nasty surprise for an investor who isn't paying attention. So since we know this risk is asymmetrical, it's lopsided, a single number for effective duration might not be telling us the whole story. We need to bring out some more precise instruments from our toolkit. And that brings us to one-sided durations. It's a pretty clever idea. Instead of just averaging the price change from rates going up and rates going down, we look at each side separately. We calculate an up duration for when rates rise and a down duration for when rates fall. We're essentially splitting that one effective duration number into two much more descriptive and useful parts.
Now, take a look at this example for a callable bond. The effective duration is 1.39. Okay, fine, but the one-sided durations? They tell a way more interesting story. The up duration is almost 2, while the down duration is less than 1. This tells you, clear as day, that this bond is way more sensitive to rates going up than it is to rates going down. A critical piece of information that the single effective duration number just completely glosses over.
Our final duration tool is key rate duration. You see, effective duration has a big, simplifying assumption that the whole yield curve shifts up or down in parallel. But when does that ever actually happen? Key rate durations let us get way more granular. We can see how a bond reacts to a change at just the 2-year point, or the 10-year, or the 30-year. This is how we spot shaping risk, the risk that the curve might twist or flatten.
This table is just a perfect illustration of why key rate durations are so powerful. We've got two 30-year bonds, and they're both callable in 10 years. Now, the low coupon bond, it's probably not getting called. So, no surprise, its risk is all packed at the 30-year point. But get this, look at the high coupon bond. It's almost guaranteed to be called in 10 years. So what happens? Its main interest rate risk completely shifts from its 30-year maturity to its 10-year call date. It's basically a 10-year bond now, and key rate durations are the only tool that lets you see that switch so clearly.
Okay, let's switch gears for a second and apply these ideas to another really common security you'll see: capped and floored floating rate notes. Now, the options here are a little different. Unlike calls and puts, they get exercised automatically, like clockwork, based on where the reference rate is.
This right here is the first thing you need to memorize. A cap protects the issuer from having to pay out too much if rates shoot up, so it's an option the investor sells to the issuer. A floor, on the other hand, protects the investor from earning too little if rates crash, so that's an option the investor owns. Who holds the option is the absolute key to valuing them.
And that leads directly to the valuation. So think about it. Because the cap is an option that benefits the issuer, not you, it has to make the bond less valuable to you. So, to find the value of a capped floater, you take the value of a straight floater and you subtract the value of that embedded cap. And for a floored floater, it's the exact opposite. You would add the value of the floor you own.
So, how do we actually calculate the value? Well, the good news is it uses that same arbitrage-free binomial tree framework you already know. You build your interest rate tree. But instead of wondering if an issuer is going to call the bond, you just check if the rate at each and every node hits the cap or the floor. If it does, you adjust the coupon for that period, and then you just roll everything back to today using backward induction.
And here's the final answer from the example in the reading. A normal, uncapped floater would be worth par, right? 100? But because this one has a 4.5% cap on its coupon, some of those potential high coupon payments get chopped off. The value of those lost payments brings the bond's price down to 99.761. That little difference, about 24 cents on the dollar, is literally the price the investor is paying for having sold that cap option to the issuer.
Let's just pause on this quote for a moment, because this is a golden rule. It's one of those fundamental takeaways you should walk away with. Having a call or a put option always, and I mean always, acts to lower the bond's maximum potential duration. The option puts a ceiling or a floor on the price, and that automatically dampens how sensitive it can be to interest rates compared to its option-free twin.
Let's end with a practical question that pulls all these ideas together. Put yourself in the portfolio manager's seat. Which scenario gives you a bigger headache? If you own a portfolio of callable bonds and rates just tank, your upside is gone because the issuer is just going to call them all away from you. Or if you own puttable bonds for protection and rates skyrocket, sure, the put protects your downside, but you're missing out on a huge opportunity to reinvest at much higher yields. The big takeaway is that in both cases, the embedded option creates this asymmetrical risk profile that you, the analyst, have to be able to measure, manage, and master.